Hello everyone. We are going to work through another example here. We're using multiple distinct recursive calls. In this example we have here, it looks similar to a Fibonacci example, except we've added in a couple of additional things. Our subtractions that we're doing are a bit worse, and our additional cost is Cn. But like we saw, we are almost always going to bound this below. So we bound below as a first step. To bound this below, we identify which of the two recursive calls is the smaller one. The subtracting more means that we make it smaller. So the smaller of the two recursive calls here is the t of n minus 6. So when bounding it below, we have that t of n is greater than or equal to t of n minus 6 plus t of n minus 6 plus Cn. So we replace the larger of the two, t of n minus 3, with the smaller of the two, which is t of n minus 6. Then we can again bound it below even further by dropping the Cn. So if I group those together and drop the Cn, then I keep bounding it below. I'm actually going to go through the substitution faster here and show you the way I typically do these problems on my own. So the way I would proceed here is I would do a substitution, t of n greater than or equal to 2, and do the substitution in place. If I plug n minus 6 in, I would get 2t of n minus 12 in that expression. So I just do the substitution in place. That's by plugging n minus 6 into the equation above for all of the copies of n. Then maybe I do a bit of simplification. I have t of n greater than or equal to 4, t of n minus 12. I'll then do another substitution, again in place, greater than or equal to 4, times perform a substitution. Plugging n minus 12 into the red equation, I get 2, t of n minus 12 minus 6, which is n minus 18, and then distribute the 4. T of n is greater than or equal to 8, t of n minus 8, and now we need to identify a pattern. In which equations, I'm going to quickly denote them here with green dashes. In all of those green dashed equations, I need to identify a pattern. 2, 4, 8 for the coefficient. That's pretty straightforward. So we have that for any value of k, t of n is greater than or equal to 2 to the k for the coefficients out front. The stuff inside of t is minus 18, minus 12, and minus 6. Hey, those are multiples of 6. So that's t of n minus 6k. Now, we need to find out when does this stop. Let's even do it in a different color to avoid confusion. This stops when the thing inside of t, which is n minus 6k, equals our base case. What's our base case? If we scroll up, our base case was 0, so we set that equal to 0, and solve for k. Add by 6k, divide by 6. We get k equals n over 6. So, let's plug that in. We have t of n greater than or equal to 2 to the n over 6 times t of 0. And I know t of 0 is c. So t of n is greater than or equal to c times 2 to the n over 6. And hey, look, that's an exponential lower bound. So, therefore, t of n is in big omega of 2 to the n over 6. And that's sufficient for this problem. Because it is an exponential lower bound, we are done with the problem. And hey, that's not too bad. If you notice, this example is nearly identical to the Fibonacci example, so there's very little cleverness get involved in any of these problems. You just need to identify when can you bound it below and get an exponential lower bound. And that will typically occur when you have multiple recursive calls that look like t of n minus something. So that's all we have to do for this problem. Nice and quick. Not that bad, right? Hopefully.